Hi, welcome all to the online classes. I'm Mukesh Bhardwaj. Today going to present a topic, conductors and insulators in engineering physics, BTech agriculture first semester. So conductors and insulators are the basic materials which are abundantly available on the earth and are having a vast or variety of applications. So we are starting with conductors first. Conductors. What is conductors and insulators? Distinction between or difference between metal insulators and semiconductors. There are many energy bands in solid as there are energy levels in parent atom. The electrical conduction properties of solids are concerned. Only the valence band and the conduction band energies of the electron are considered. Filled bands and completely empty bands do not contribute to electrical conduction. The electrons in the innermost fill shell do not take part in the conduction process. The electrons in conduction band are free and move easily under an electric field. The electrons in valence band are attached to the lattice and are not free to move. So, the main difference between the insulator, conductors, and semiconductors is just based upon the energy bands configuration. Next, if they acquire sufficient energy to cross the forbidden gap, e.g., they occupy the conduction band states are available for conduction. On the basis of band theory, solids are classified into three categories: insulators, semiconductors, and conductors. So, a conductor is an object or type of material that allows the flow of charge in one or more direction. Materials made of metal are common electrical conductors. Electrical current is generated by the flow of negatively charged electrons, positively charged holes, and positive or negative ions in some cases. Conduction materials include metals, electrolytes, superconductors, semiconductors, plasmas, and some non-metallic conductors such as graphite and conductive polymers. Copper has high conductivity. Copper, silver, gold, aluminum are the examples of good conductor. In electrical engineering, a conductor or electrical conductor is defined an object or type of material that type of material that allows the flow of charge in one or more direction. Uh, More directions. Materials made of metal are common electrical conductors as metal have high conductance and low resistance. Electrical conductors allow electrons to flow between the atoms of that material with drift velocity in the conduction band. Conductors may be metals, metal alloy, electrolyte, or some non-metals like graphite and conductive polymer. These materials allow electricity to pass through them easily. How does a conductor conduct current? The substance of the electrical conductor atom must have no energy gap between its valence band and conduction band. The outer electrons in the valence band are loosely attached to the atom. When an electron gets excited due to the electromotive force or thermal effect, it moves from its valence band to the conduction band. The conduction band is the band where this electron gets its freedom to move anywhere in the conductor. The conductor is formed of atoms, thus as whole the conduction band is in abundance of electrons. In other words, it can be said that metallic bonds are present in the conductors. These metallic bonds are based on the structure of positive metal ions. These structures are surrounded by an electron cloud. When a potential difference occurs in the conductor across 2 points, the electron gets sufficient energy to flow from lower potential to higher potential in this conduction band against a small resistance offered by this conductor material. Electricity or current flows in the opposite direction of the flow of electrons. Now, insulators. An electrical insulator is a material whose internal electric charge do not flow freely. Very little electric current will flow through its under the influence of an electric field. This contrasts with other materials, semiconductors and conductors, which conduct electric current more easily. The property that distinguishes an insulator is its resistivity. Insulators have higher resistivity than semiconductors or conductors. Electrical insulation is the absence of electrical conduction. Wood, plastic, rubber, wool, paper, wax, glass, ebonite are examples of insulators. Insulators are materials that inhibit the flow of electron current. The opposite of conductors, which allow electric particles to flow freely, insulators are implemented in household items and electrical circuit as protection. Thermal insulation is similar but constricts the flow of heat rather than electricity. Insulators possess a high resistivity and low conductivity. Their atoms have tightly bound electrons that do not move throughout the material. Because the electrons are static and not freely roaming, a current cannot easily pass. In addition to protecting loss of current, insulators make an electrical current more efficient by concentrating the flow. These are some examples of conductors and insulators. Electrical conductors: silver, gold, copper, steel, seawater, as you see in the diagram. Electrical insulators: rubber, glass, oil, diamond, dry wood. Crystals now being used in devices are grown up with concentration of Mohs impurities of less than 1 part in 10 billion. Such impurities or such purities require careful handling and treatment of material at each step of manufacturing process. Elemental germanium silicon are obtained by chemical deposition of compounds such as germanium oxide, silicon chloride, and silicon hydrochloride. Once the semiconductor material has been isolated and preliminary purification steps have been performed, it is melted and cast into ingots. Upon cooling from such a casting process, the silicon and germanium is polycrystalline. The atoms are arranged in diamond lattice over small regions of the ingot. Since this is the natural structure of the material, however, unless some control is maintained over the cooling process of crystalline, regions occur with essentially random orientation. For the crystal to grow in a single orientation, it is necessary to maintain careful control over the boundary between the molten material and the solid during cooling. In the fabrication of silicon integrated circuits, it is economical to use very large silicon wafers so that many IC chips can be made simultaneously. As a result, considerably research and development have gone into methods for growing very large silicon crystals. The preparation of intrinsic silicon is less difficult than that for germanium because more impurity ions can be tolerated in states within energy gap because of its wider energy gap before it is shows extrinsic behavior. Silicon Silicon is used for majority of rectifiers, transistors, and integrated circuits. On the binary or of the binary semiconductor, two groups have come into the prominence. The second and sixth group include materials like zinc sulfide, zinc telluride, cadmium sulfate, and many more. The energy gap of these materials are usually high. Second and sixth group has 2 plus 6 equals to 8 electrons to be shared by the atoms. 4 covalent bonds per atom are generally formed, but some compounds are atomic in nature. So, we had discussed a lot about the semiconductors in detail. Now we are going to start with the topic superconductors. So, to understand the superconductor in detail, we first to understand the definition of superconductivity. Superconductivity is a state of matter exhibit at a very low temperature where the resistivity of the material drops to zero and become perfect diamagnetic. In the previous lectures, we had studied about the classification of magnetic materials, and we know the property of a diamagnetic material. Superconducting state is influenced by temperature, current, and magnetic field. So these are the some three basic parameters in which the superconducting state is influenced. First is by temperature, second is by current, third is the magnetic field. There exist critical values for these three parameters above which the material passes into normal state. It is designated for use in the field of medicine and particle physics. It is being tried for use in transportation and transmission of power. Maglev, if you hear the name magnetic levitation train, the basis for the magnetic levitation train is superconductivity. And a magnetic levitation train is a concept of transportation in which the movement of train is just above the earth, a few inches or few centimeters above the track, to provide the faster speed and very less time consuming and very controlled in fashion. So recently the high temperature ceramic superconductor raised the hopes of using superconductors in making more efficient and smaller electrical and electronic devices at normal temperature. At the state of material in which it has zero resistivity is called superconductivity. So the conclusion is that a state of material in which it has zero resistivity, as such we know the resistivity is the parameter of any material which is very constant. It cannot be changed and or it cannot be vary. But if any state of the material in which its resistivity is zero, then it is called superconductivity. Superconductivity was discovered in 1911 by Professor H.K. Owens. Who observed that resistivity of mercury vanished completely below 4.2 Kelvin. The transition from normal conductivity occur over a very narrow range of temperature of the order of 0.05 Kelvin. So, now the phenomena of superconductivity or superconductors. Metal are good conductors of electricity. as they contain large number of free electrons. As a result, low resistance offered by them to flow current is attributed to the scattering of the free electrons by vibrating ions of the lattice. As temperature increases, the amplitude of the lattice vibration increases and causes more scattering of electrons, leading to more resistance. Even at 0 Kelvin, that is minus 273 degrees centigrade, metal offers finite resistance. It's called residual resistance. It is attributed to scattering of electrons by impurities and crystal defects present in the material. The variation of resistivity of normal metals with temperature is shown in the next slide. This is how the variation of resistivity of metal and the superconductor varies with the temperature. So at 0 Kelvin, the metals have some sort of resistivity at 0 Kelvin. And if you when increase the temperature, then the electrical resistivity of metal is exponentially increasing in a very few order. But if I talk about the superconductors, so at the critical temperature which is shown in the figure, that is Tc, the electrical resistivity is shown as in the figure. It indicates the existence of residual resistance, that is rho r. H own was explained the behavior of metals at very low temperature. The electrical resistance of highly purified mercury drops suddenly to zero at temperature of 4.2 Kelvin. This transition is reversible. When the metal heated above the transition temperature of 4.2 Kelvin, the mercury regains its resistivity. H. named the phenomena as superconductivity. Now, superconductivity was a strictly low temperature phenomena. Some ceramic were found to exhibit superconductivity at high temperature of about 120 Kelvin. It was discovered for lead, zinc, aluminum, and other metal alloys and number of alloys. Superconductivity is a phenomena in which the electrical resistance of materials suddenly disappears below a certain temperature. The material that exhibits superconductivity and which are in the superconducting state are called superconductors. Superconductivity appears at low temperature and in magnetic field lower than a particular level. So, the figure we had seen shows that an example of the variation in electrical resistivity with the temperature. The temperature at which superconductivity appears is called the critical temperature or transition temperature. Superconductors are material which show superconductivity under certain condition of temperature and magnetic field. The state in which the superconductor does not show superconductivity is called normal state. A finite jump in the specific heat is observed at the critical temperature. Hence, a change from normal to superconducting state and vice versa is second order phase transition. It shows or it's shown experimentally that entropy is lower in superconducting state than a normal state. Entropy is lower in superconducting state than normal state. Now, Meissner effect. A Meissner effect is a fact that discovered in 1933 that not only did superconductor exhibit zero resistance but also spontaneously expel the magnetic flux when cooled through the superconducting transition. That is, they are also perfect diamagnetism. That is, they are also perfect diamagnets. We call this Meissner effect. Meissner effect is not consequence of zero resistance and Lenz's law. The flux is expelled as the superconductor is cooled in constant magnetic field. There is no time rate of change of magnetic induction. Lenz's law does not apply. So Meissner effect is nothing. The explanation of Meissner effect is that simply any superconducting material when placed through the magnetic line of flux or in between the magnetic line of flux, then at the state of superconductivity, the material does not allow the magnetic flux line to pass through it, and all the magnetic lines of flux expelled around the superconducting material, and this effect is known as Meissner effect. So it is a perfect diamagnetism is an independent property of superconductors and shows that superconductivity involves a change of thermodynamic state, not just a spectacular change in electrical resistance. This is conceptually deepest property of superconductivity. So Meissner effect is the deepest property of superconductivity. Next, transition temperature. The temperature at which normal material suddenly changes into superconductor is called transition temperature, which I had already told, that critical temperature. It is also called as critical temperature. Now, critical magnetic field. Superconducting states depend on the strength of the magnetic field in the material is placed. Superconductivity state or superconducting state depends on the strength of the magnetic field in which the material is placed. So, there is a short review or short explanation to understand this figure. Removal of the superconducting state does not only occur by raising the temperature, but also by subjecting the material to a magnetic field. The critical value of magnetic field for the destruction of superconductivity. Critical magnetic field is denoted by Hc in the figure. It is a function of temperature Tc at T equals to Tc. Hc is equals to 0. With only some deviation, the critical field Sc varies with temperature according to the parabolic law. So, the parabolic law or the equation govern this figure is given as Hc is equals to H naught 1 minus T upon Tc whole square. H naught is the critical field at absolute zero and Tc is the transition temperature. For any particular superconductor, the shape of the variation of Hc with temperature is shown in the figure. The magnetic field which causes a superconductor to become normal from a superconducting state is not necessarily an external applied field. It may arise as a result of electric current flow in the conductor. In long superconductor wire of radius r, superconductivity may be destroyed when a current I exceeds the critical value Ic, which at the surface of wire will produce a critical field Sc given by Ic equals to 2 pi r Sc, called Silsby rule. So, Ic equals to 2 pi r Sc is known as Silsby rule. Now next, it vanishes if a sufficiently strong magnetic field is applied. The magnetic field which is essential to regain the normal resistivity is called critical magnetic field. When the applied magnetic field exceeds the critical value, the superconducting state is destroyed and the material goes into the normal state. The value of critical magnetic field varies with the temperature. So, if I just going back to show the diagram once again, Tc1 and Tc2 are some critical temperatures. That means the magnetic field is directly depending upon the temperature condition. And as you are seeing, this graph is showing some parabolic view, and if I'm talking about HC1, TC1, or if I'm talking about this point HCO and this point, last point, so any point TC, you may call it TC and this is called HC. So below to these points, the material is behave like a superconducting material, or it is in the state of superconduction. Below to these extreme points, the normal, when you go on increasing the temperature, the magnetic effect vanishes out and the critical magnetic field SC is also moved out or removed out, and the material convert into the normal state. But before to these points or to these states, it start behaving like a superconducting material. So some materials having the different critical temperatures, which is denoted by TC1 and TC2. It shows the dependence of critical magnetic field on temperature in a typical semiconductor. At a temperature below TC, in absence of magnetic field, the material is in superconducting state. When magnetic field is applied and its strength reaches the critical value, material is in superconducting state. When magnetic field is applied and its strength reaches the critical value SC, the superconductivity in the material will be disappears. At any temperature T less than critical temperature, the material remains superconducting until a corresponding critical magnetic field SC is applied. When the magnetic field exceeds the critical magnetic field, the material goes into a normal state at particular temperature. Now, the quiz and questionnaire is related to the superconductivity. Before attempting the quiz, I would like to give a brief review or introduction about types of superconductors. From their magnetic properties, superconductors are classified into two groups. As in semiconductors, the superconductors are also classified into two groups. Those that show perfect diamagnetism magnetisms up to the critical magnetic field or SC and go to the normal state as shown in the previous figure, or called type 4 superconductors. Soft metals such as lead or indium belong to this group. The critical field of these superconductors are low, even in tantalum, which is highest critical field, has value at 0 Kelvin of mu naught SC 0 at 0 SC equal SC at 0 equal to 83 MB MT, and these materials are not suitable for field application. They are also called superconductors, soft superconductors, or ideal. They have low melting point. These materials obey Silsby rule and shows Meissner effect. The transition from normal to superconducting state is sharp. They have low value of field, critical field and critical temperature, and they are also known as type first superconductor, type first. So we say that superconductors are basically categorized in two categories. First is type first and second is type second, or the first one is also known as soft superconductors and the second type is known as hard superconductors. Sorry. On the hard, on the other hand, hard metals and alloys have different magnetization characteristics as shown and are called type second superconductors or hard superconductors. They are characterized by high transition temperature, high critical field, incomplete Meissner effect, breakdowns of Silsby rule, and or broad transition region. The upper critical fields of some materials of this type are very high. So this is the classification of two type of superconductors. Now, some superconducting materials like aluminum, indium, lithium, Nb, lead, Re, strontium, tellurium, Tc, vanadium, and their critical temperature where they behave like a superconductors. For aluminum, it is 1.19. For indium, it is 3.41 Kelvin. For lead, it is 7.18 Kelvin. Since 1911, superconductivity has been found and occur in some 27 metallic elements and hundreds or perhaps thousands of alloys and compounds. Some of these materials are listed or explained. Other properties like frequency effect. Superconductivity is observed for DC and up to radio frequencies. It is not observed for higher frequencies. For a superconductor, the resistance is zero only when the current is steady or varies very slowly. When current fluctuates or alternates, small absorption of energy roughly proportional to rate of alternation occurs and is not yet fully understood. When the frequency of alteration rises above 10 MHz, appreciable resistance arises, and at infrared frequencies 10 to the power 13 Hz, the resistivity is same in the normal and superconducting states and is independent of temperature. Entropy. Entropy is the degree of randomness that is increases on going from superconducting state to a normal state. Thermal conductivity. In an ideal superconductor, there is a marked drop in the thermal conductivity when superconductivity sets in. In non-ideal superconductors, an increase in thermal conductivity on becoming superconducting has been observed in few specimens. Isotopes effect. It has been observed the critical temperature of superconductors varies with isotopic mass. So, if I talk about the applications, superconducting materials are of interest because they promise low joule heating losses in electrical power generation and transmission system. Today, superconducting magnet technology is in the mature stage. Many large magnets for nuclear fusion experiments have been constructed. The superconducting magnetic resource imaging, that is MRI, market is going steadily. An experimental magnetic levitate train is under development as a commercial transportation system. Superconductivity is also entering in the field of electronics. Superconductivity or superconducting technology has the inherent ability to provide devices, components, and systems which can greatly reduce overall system weight, volume, and input power. Superconductivity or superconducting technology can provide breakthrough in spacecraft design and performance, many devices. Superconducting wires of MBZR produced in 1961 could produce a magnetic field of 4 Tesla. With the present day technology, we can have wires of SNTI and V3GA which can produce field up to 20 Tesla. So the conducting magnets find application in the following areas: magnets for nuclear fusion, magnets for high energy physics, generators and motors, magnetically leviated transportation, superconducting magnets for energy storage, magnetic resonance imaging and other application in field of medical science. Superconducting materials are used as electronic switching devices called cryotrons. Superconducting materials which is used as switches or switching devices are called cryotrons. So this is all about superconductivity and superconducting materials and types of superconducting materials. Now it is a quiz time. A solid that offers no dash passage of electricity is called superconductors. Conductance, inductance, resistance, impedance. So resistance is the right answer. The solid that offers no resistance passage, zero resistance is offered to the electricity, they are called superconductors. The phenomenon of superconductors was first discovered by Kamerlingh Owens. Superconductors are discovered in the year 1911. The earliest superconductors to be studied elaborately is niobium alloy. The shifting of electrons in superconductors is prevented by quantum effect, threshold energy level, energy barrier, orbitals. So the shifting in electrons in superconductors is prevented by quantum effect. The electrons head in dash direction. The electrons head in same direction. The normal metal passes into superconducting state at critical temperatures. Okay. The normal metal passes into superconducting state at a critical temperature, that is Tc. Based on magnetic response, superconductors are of two types. We had discussed that. First type and second type, or soft type or hard type. Ideal superconductors completely become dia, ferro, ferri, para at superconducting states. The ideal superconductor exhibits Meissner effect, mesomer effect, monomer effect, mesmeric effect, Meissner effect. The hard superconductors are those in which ideal behavior is seen up to critical magnetic field, higher, lower, moderate, zero. 12. This function has superconductors at critical temperature of the constituents of this material, that is yttrium, barium and copper, are in preparation of superconductors by ceramic methods by homogeneous mixture of the oxides dash in their molar ratios. Annealing the homogeneous mixture to room temperature to retain its composition, structure, its properties, composition, structure, its properties, all the three. So these are some questionnaires, and this is all about the topic. Now, thank you all. In next lecture, we are going to start with diodes, how the diodes form, what are the construction details of diode, what are the application of diodes, and working of diode, and then types of diodes. Thank you.